So today I want to talk about torque, and torque is the cause of rotational motion. We've been discussing a lot about rotational motion, but we've just been sort of assuming that it was already going on and dealing with it from there. Now I'd like to talk about what causes the rotational motion in the first place, or causes a change in the rotational motion of the object. So that is torque. Torque is the tendency of a force to rotate an object about an axis. Torque is actually a vector, and the vector will point along the rotation axis, but we're not going to worry too much about the direction of the vector here. We're just going to worry about the magnitude of the vector and the tendency of that vector to cause an angular acceleration. So the equation for torque is torque, which here we use the Greek letter tau to symbolize, is equal to r times F times the sine of phi. Okay, let me define these terms. F is the force that causes the rotation. R is the line or distance that connects that force with the axis of rotation. And then phi is the angle between the force and that line that connects the axis of rotation, R. So these are the things that you can see in this drawing here. Now, we call this R perpendicular the moment arm or the lever arm of the force. And the R perpendicular is equal to R times the sine of phi. And your book talks a lot about it like it's some magical thing, but really it's just R sine phi, okay? And that's called the moment arm. Now, you might have experienced, let's use the example of opening a door, okay? So the rotation axis for a door is the side where the hinges are connected. So there's three things that can affect how easy it is to open the door. How hard you push, okay? The distance from the axis of rotation, you've probably noticed that it's a lot easier to open the door the further you push from the axis of rotation, and also the angle at which you apply the force. You might have noticed that if you meet the door head-on and push directly into the door, that's the easiest place to open the door, is the easiest way to open the door. Whereas if you're sort of standing to the side and trying to open the door for someone else and pushing at an angle, that makes it a little harder to open the door. Okay, so all of those things, of course, the force, the harder you push, the easier the door opens. That makes perfect sense. The distance from the axis of rotation is the maximization of that moment arm. So the longer you make the moment arm, the easier it is to cause the torque. And the angle is the sine of phi. If you push perpendicular to the plane of the door, that makes phi 90 degrees, which makes the sine of phi 1, which maximizes that sine of phi. So those are the three things that cause a torque. Now, any horizontal component of the force, the cosine of phi, so if you multiplied F times the cosine of phi, any of that will not produce a rotation. Okay. Now, torque will have a direction. If the turning tendency of the force is counterclockwise, we're going to go with that as a positive torque. And if the force causes a clockwise rotation, then we're going to call that a negative torque. Okay, now like I said, the torque is a vector which is going to point along the axis of rotation. All right, but for the purposes of our discussion here, let's just remember that counterclockwise rotations we've defined as positive, and so that's a positive torque, and clockwise rotations we've defined to be negative, and so that's a negative torque. Now, if you have someone else pushing on the door too, all right, if you're both pushing to make the torque in the same direction, then that'll of course make it easier to open the door. And that's because torque is a vector and there's a vector sum to it, all right? Whereas if you have somebody on the opposite side of the door pushing against you, that makes opening the door much, much harder. So basically, you can sum up the torques in a vector kind of way, just like you do any other vector. Remember, counterclockwise positive, clockwise negative. So to sum up, forces can cause a change in the translational motion, and that equation is given by Newton's second law. Torques will cause a change in the rotational motion, okay? And then that's given by the RF sine of phi equation that we just described. Now the units will be Newton meters because the equation is R times F, right? But don't confuse that with the joule. The units for torque are reported in Newton meters and are not changed to joules because it's understood that while the units are similar, Newton meters, torque's not really an energy. let me do an example problem with the equation that I've just given you, and hopefully this has some sort of resonance for you in your personal day-to-day life and experiences. You've probably noticed that it's pretty hard to hold objects out at a 90-degree angle to your body, whereas if you hold them straight down, it's a lot easier. And the reason for that is the torque on your shoulder. So this example talks about that. An athlete at the gym holds a 3-kilogram steel ball in his hand, and his arm is 70 centimeters long, and the arm itself has a mass of 4 kilograms. So what's the magnitude of the torque on the athlete's shoulder if he holds his arm straight out to the side parallel to the floor, or if he holds his arm straight, in other words, no bend in his elbow, but 45 degrees below the horizontal? Okay, so let's do part A first, which is where the athlete has his arm straight out. Now, I'm a terrible artist, so this is my athlete, this lovely little stick figure right here. Okay? Now, the mass of the arm and the mass of the weight both have to be considered. They're both forces are going to be due to gravity, and they will both cause a torque on the shoulder. Now, because of the mass of the arm is an extended object, so we're going to say that that acts at the center of mass of the arm, which we talked about in one of the previous lectures, the center of mass. And of course, that'll be roughly in the middle of the arm for the purposes of our calculation. So I've drawn the vector for gravity here at the middle of the athlete's arm, and of course that would be F is equal to mg, right? Now, the steel weight, which I've drawn here as a little green circle, that'll be at the end of the athlete's arm, and that'll also have a vector of mg, but this time the mass is 3 kilograms. So the sum of the torques here, the angles for each of these things are going to be 90 degrees. So the sine of 90 is 1, okay, and so that I've just put in as a 1. So the torque will be the distance from the axis of rotation, here the shoulder, to the point of application of the force, right, times the magnitude of the force itself, times the sine of 90 degrees, which is 1. And there's 2 torques, so I'm going to sum them up. So the first one is 0.35 meters, because his arm is 70 centimeters long, and half of that is 35 centimeters, which is 0.35 meters, times 4 kilograms, which is the mass of the arm, times 9.8 meters per second squared, the acceleration due to gravity. So that's the first one. Now, they're both going to cause a rotation in the same direction, so I'm going to sum them both up, plus 0.7 meters times 3 kilograms times 9.8 meters per second squared. If I sum those two things up, I get 34.3 newton meters for the torque. All right, so that's the answer to part A. Now let's compare that to the arm at a 45-degree angle to the horizontal. Yet again, I'm going to sum the torques. Yet again, it's halfway down the arm for the distance, or all the way down the arm for the distance. But now the only difference is I'm doing the RF sine of phi, and the angle in between the force and the line connecting the axis of rotation, the shoulder, to the force, that angle is now 45 degrees. So here I have 0.35 times 4 kilograms times 9.8 meters per second squared times the sine of 45. That's for the mass of the arm. And then plus 0.7 times 3 times 9.8 times the sine of 45. That's for the weight in his hand. When I sum those two numbers up, I get 24.2 newton meters. So the torque is much less when the arm is at an angle than it is when it's straight out. And that's, of course, why it's so hard to hold objects straight out from your shoulders, because the torque is maximized when that's happening. Okay, now let's think about circular motion. All right, we've already talked about how circular motion has two kinds of acceleration. There's the centripetal acceleration, which is the acceleration that keeps the object in its circular path and always points in towards the center of the circle. Even if the object doesn't change its speed, it's still got that acceleration because it's constantly changing its direction. There's also the tangential acceleration. If an object changes speed while in its circular path, then it will have a tangential acceleration. All right? Now, any force that's causing a torque is going to be tangent to a circular motion here. All right? So it'll be a tangential force. So let's write this out in terms of the torques. So the sum of the torques acting on the object will be equal to the sum of any tangential force acting on that object times r. That goes with our RF sine of phi definition that we used a little bit back. If I write that in terms of Newton's second law, where F is equal to ma, then the sum of the torques is the mass times the tangential acceleration times r. All right, so let's put this in terms now of the angular acceleration that we defined earlier. Remember that the angular acceleration is equal to the tangential acceleration divided by the radius of that circle. So if I'm plugging in for my tangential acceleration, I'll plug in alpha times r. So the sum of the torques will then be m a tangential times r, which is equal to m r times alpha times r again. And then we can pull that r in and we get mr squared times alpha. Well, this constant, or this expression pops up so often in circular motion that we're going to name it. And we're going to call it the moment of inertia of the particle. So then we can write the sum of the torques as I times alpha, where I here stands for the moment of inertia. So the torque is directly proportional to the angular acceleration, and the constant of proportionality there is the moment of inertia. The moment of inertia for a system of point particles, if there's more than one, will be equal to the sum of mi times ri squared, where ri here is the distance from the axis of rotation, right, your moment arm, and then times mi, which is the mass of the particle. The units, the dimensions for the moment of inertia, are going to be kilograms times meters squared in SI units. So what this is saying is the distribution of the mass matters, all right? For example, here in this drawing, we've got these two discs, okay? They have kind of the same shape. They're cylinders. If you wanted to use the same mass in each disc, you could make a disc that has less thickness but has a larger radius, okay? Or you can make a disc that is longer with smaller radius. And you can see how these two different distributions of mass would result in the same mass but with different shapes. But you might notice that if you're looking at how the mass is distributed, the longer cylinder will have a lower moment of inertia because the distance from the axis of rotation in the moment of inertia expression is squared. So that means there's a very large dependence on it. So if your mass is distributed in a long, thin cylinder rather than a wide cylinder, then it will have a lower moment of inertia. It's harder to rotate things if the distribution of the mass is further from the axis of rotation. So you can think of the moment of inertia as an inertia or a resistance to a change in rotational motion. And that is dependent upon two factors: the mass, the total mass of the object, and then how that mass is distributed. If something is further from the axis of rotation, it will be more difficult to start that object rotating or to change its rotation once it's going. Let me show you an example problem where you're finding the moment of inertia for a distribution of point masses. Here's the same example in terms of the masses that I used for the center of mass, but now we're going to find its moment of inertia, assuming that the axis of rotation is the y-axis. So what would happen is point A would be along the axis of rotation, and B and C would rotate out of it. In other words, it would come out of the screen at you and then go into the screen on the opposite side if it were rotating. Okay, so here we have the 200, 300, and 100 gram masses forming a little triangle, and the axis of rotation is the y-axis. So going with the definition of the moment of inertia as the sum of mi ri squared, for the 2.2 kilogram mass, the 200 gram mass, that is on the axis of rotation, which is the y-axis. So the distance to the axis of rotation is 0. So I have 0.2 times 0 squared. Whereas the 300 gram mass, or 0.3 kilogram mass, that's 10 centimeters from the axis of rotation, and so it's 0.3 times 0.1 squared. The 100 gram, or 0.1 kilogram mass, is also 10 centimeters from the axis of rotation, and so that's 0.1 times 0.1 meters squared. So if I sum all that up, I get 0.004 kilograms meters squared for the moment of inertia for these point masses. You can also find the moment of inertia for extended objects. However, you need calculus to do it. So I'm not going to ask you guys to do that in Physics 1103. will give you a chart of the values for extended objects, okay? And you should know how to use and read this chart. There's a similar chart in your book. Just to summarize for a couple of them, if you've got a solid disk or cylinder, then that's 1/2 the mass of the cylinder times the radius of the cylinder squared. Okay? Now let's compare that to a thin spherical shell. Going along with the definition of the moment of inertia, that we remember that the distance from the rotation axis is squared, and so there's a large dependence on that. That one is mr squared. So you can see that if you compare a solid disk or cylinder, you've got half the moment of inertia than you do if it's a hoop or a thin spherical shell, if the masses are the same. Okay? And that's because in the thin spherical shell, all that mass is at a larger distance from the axis of rotation than if the shell is filled in. That makes sense, I think. Now, if you have an extended object, but the axis of rotation isn't exactly like what it says to do in this chart, then you probably will be able to use what's called the parallel axis theorem. Okay? In the previous examples, the axis of rotation coincided with the symmetry axis of the object. Okay? But for some arbitrary axis that's parallel to the symmetry axis, then you can use this definition. The moment of inertia in the new way that it's shown is equal to the moment of inertia in the chart, the center of mass moment of inertia, plus the mass of the object times d squared, where d is the distance from the center of mass axis to that arbitrary axis. Okay? The distance between the axes. Let me show you one here. Okay, if you look in this chart, if you're rotating a long thin rod with a rotation axis through the center, say like a baton, okay, for a acrobat or something, okay, then that's 1/12 ml squared, where L is the length of the rod and m is the mass. But now let's say that instead of rotating about its center, you want to rotate it about one end. Okay, so that's this one. So the moment of inertia of the rod about its center would be 1/12 ml squared. If you were rotating it about the end, d, the distance from the center to the end, which is the new axis of rotation, would be 1/2 the total length of the rod. So your new moment of inertia would be 1/12 ml squared plus the mass of the rod times the distance d squared, which is L over 2 squared. And then when you add those two things together, you get 1/3 ml squared for your new moment of inertia. Okay, now, to solve some of the torque problems that you'll see in this chapter, it's often required to equate the two equations that we have for torque. Remember, the first equation we defined straight off, and that was RF sine of phi. And then you can set that equal to the moment of inertia times alpha, which was the second equation that we defined for torque. And lots of times you need to use both of these equations in order to solve your torque problems. Let me give you an example. A rope is wrapped around a 3 kilogram cylinder of a radius 10 centimeters that's free to turn about its axis. The rope is pulled with a force of 15 newtons. The cylinder is initially at rest at time t is equal to 0, and now you need to find the torque exerted by the rope and the angular acceleration of the cylinder. And then find the angular velocity of the cylinder at a time t is equal to 4 seconds. Okay, so this might seem a lot, but what we're going to do here is use RF sine of phi equal to I alpha. We're going to solve for alpha, and then we're going to use our kinematics equations, our rotational kinematics equations, to find that angular velocity at a later time. So that's our strategy. Okay, so here we go. Torque is equal to RF sine of phi is equal to I alpha. Now, it said in the problem that we used a 15 Newton force at a 10 centimeter distance from the axis. So that's the RF sine of phi part. Okay? Now, if you're pulling something with a string, then what's going to happen is the tension of the string will cause that tangential force, and that'll always be at a 90-degree angle to the rotation axis. So sine of 90 will be 1. So torque, RF sine of phi, will be 0.1 meters, 10 centimeters, times 15 newtons, which is the force, and that'll give us a torque of 0.15 newton meters. And now we set that equal to I alpha, okay? Now, if you use your chart, it says that it's a cylinder, okay? And it's free to turn about its own axis, its symmetry axis, which would be right through the center of that cylinder. So if you remember from the table, and if not, you could always look it up when you're doing your own problems, that moment of inertia for that extended object is 1/2 mr squared, where r is the radius of the cylinder. So you've got I, which is 1/2 times 3 kilograms times 0.1 meters squared, and then times alpha is equal to our torque, which is 0.15 Newton meters. And then you solve for alpha, and you get 10 radians per second squared. Okay, so we found alpha, but now we need to use alpha to solve for the angular velocity after 4 seconds. In the problem, it told you that the particle started from rest. It wasn't turning when the problem started. So my initial angular velocity is 0. So I can just use the kinematics equation omega f is equal to omega I plus alpha t and solve for my final angular velocity using alpha that I found in my torque equation. So I get omega f is equal to 0 plus 10 radians per second squared times 4 seconds, which gives me 40 radians per second at time t is equal to 4 seconds. Now, we're going to keep working on more examples with torque, so no fear. And one of the examples that we're going to do in class is about wheels and the torque about a wheel. I'm not going to talk too much about it at this time, but I do want to say that for wheels, for objects like wheels, on wheelbarrows or horse-drawn carts, okay? So, for example, here I have a shopping cart. He's not a horse, but close enough. It's a cart that's being pushed. What's causing the torque to turn that wheel is the static friction between the wheel and the ground. So the guy pushes on the cart, but then what really matters is that it's not on a really super slick surface. If it were on a super slick surface, the wheel would just skid over the surface, right? And it wouldn't turn the wheel. So it's the static friction between the wheel and the ground that keeps that point of contact between the wheel and the ground still enough that the wheel is allowed to turn. All right? So in this case, static friction acts tangentially to the wheel, which is parallel to the ground, causing the wheel to turn and causing the turning of the wheel. So that's for carts, things that are pushed, wheelbarrows, stuff like that. However, if you're in a car or perhaps a bicycle, then the engine or your pedaling causes that torque on the wheel that causes it to turn. Static friction allows that turning of the wheel to push the bicycle or car along, okay? For example, if I press on the gas when my car is stuck in the mud or something like that, then the wheel will turn like crazy, but the car won't go anywhere, okay? So in that case, it's the engine or the pedaling that causes the wheel to turn, and then the static friction between the wheel and the ground causes that turning to push the car forward. All right, so I hope that helps. Don't worry if it's confusing. We'll still do some more examples in class, and I'll